So if you put on, as we were saying, if you put on fixed time stepping, what's gonna happen is the software is gonna keep your time step exactly as it is shown, and it wouldn't change it, and it will keep that exact same thing throughout the simulation. But sometimes the fixed time stepping wouldn't work very well for you. For example, there are situations that you want to have smaller time steps at the beginning of the simulation, or smaller time steps at points that the flow is difficult to resolve, and in the other times you want to have it as in higher time steps. So that's when you use adaptive time stepping. In adaptive time stepping, you will give software some indicators that, based on those indicators, software will decide what would be the software at that moment. But for majority of the cases, we will keep our time stepping on fixed time stepping. So after prescribing time step, now the question is, what would be the question is what would be your the question is what would be your time step size, because that's something we as person performing the simulation has to decide about that. So the general rule of thumb is that the delta t, the time step size, should be small enough to resolve time dependent features, which means if you have a physical phenomena that is happening in a small time, for example, if you have a reaction in your system, chemical reaction that happens in, say, half a second, your time step size probably has to be 0.1 second or less than that. Meaning, if the reaction takes place in half a second, in order to properly capture that in your simulation, you gotta have enough number of time steps in there to be able to simulate it. Okay, so that's very, very important. But the question is, how can I come up with some sort of benchmark time step to start my simulation from there? That's where you use the following equation. In here, what you would do, you will calculate your time step size based on your typical cell size. So you would take a typical cell size, and the typical cell size is this cell size of the majority of the cells in the system, or the cell size of the locations that the flow is very important. So you would take that typical cell size and divide it by characteristic flow velocity. And again, we all know that one flow doesn't have one velocity, but usually what happens is you can define a flow by velocity, which means it's the dominant velocity, or the velocity which is in the places, in locations that are very important. If you divide this, it will give you an idea about this delta t. Is this delta t something solid and determined? Obviously not. This will give you just an idea about the order of magnitude of delta t. Then, based on the difficulty of the simulation, based on the phenomena happening, based on the numerical models that you will be using, you can change this time step. But this would be a very good start point. After deciding your time step, we will go to the run calculation section. So now we have decided about our time stepping method. We will keep it at fixed. We have defined our time step size. We have defined how many time steps we want to perform the simulation for. But before just starting the simulation, we have to also take care of something else, which is called maximum iterations per time step. What the maximum iterations per time step is, it comes from the logic that essentially the simulation in each time step runs same as a steady state simulation. So you remember the whole thing about performing an iterative process to come up with an accurate result. That process repeats every single time step. So you perform an iterative process, to come up with an accurate result for that time step. Then you move to the next time step and perform the same scenario again. Now, if that is the case, well, we need to define for the software how many iterations it has to perform in each time step. And obviously, again, the convergence criteria are in place in here, but we have to instruct the software how many time step size it wants to operate. Usually the number is around 20, meaning if you need more than 20, I mean around 200, 100 to achieve convergence in each time step, that means your time steps are either big or some numerical methods are not accurate enough. So try to keep this maximum iteration per time step around 20, 30, maximum 40. So after this, you start simulating, of course, and the behavior, and of course you will monitor the residuals in here, right? So when you are monitoring the residuals, the way the residuals will look like in a transient flow is very different than what it will look like in a steady state flow. So in a steady state flow, as you know, the residual starts at a very big number, and by every iterations it goes down, down, and down until it satisfies all the criteria that you have for convergence, and the simulation stops. But in here, you can see that actually you can divide. Let me open the pen. Yes, actually you can divide your residuals to some mini steady state behaviors. So what happens in here is what happens in here is these are representative of each time step. So in each time step you have an initial guess, you start iterating, and these are those 20 iterations. And have in mind, it does not necessarily fill all the 20 iterations, because it might achieve convergence way before those 20. And as soon as it achieves the convergence, because you have convergence criteria in place, it will move to the next time step. So it starts converging, start going down, the residuals start going down, and at some point around here, all the results satisfies basically the criteria for convergence, and we move to the next time step. But as we move to the next time step, since the situation is changed now, your residuals are going to shoot up again. And once they shoot up again, we have to perform iterations to bring down the residuals and come up with a definite result for that section for that time step. And this goes on and on for the number of time steps that you have prescribed in here. So generally speaking, for a transient flow, we usually use Paiso scheme for pressure velocity coupling. Select the number of iterations per time step to be around 20. And as I said, you can go to 30, 40, 50 even. But if you have to go to 100, 200 to achieve basically convergence in each time step, although there is nothing wrong with it, but generally speaking, it means instead of increasing number of iterations, there is a better way of achieving convergence, which is usually by decreasing the time step size. And remember, the simulation converges easily and more accurately as you make the time steps smaller and smaller. But of course, you can't always do that, so we have to stick to our engineering guess. Remember the initial guess, initial conditions are as important as boundary conditions in here. They are not anymore initial guesses. They are the state of your system at time to equal to 0. And of course, you will understand this whole process much better once we perform a simulation for it. So the transient part is now finished, and we're gonna move in our next video to our second part of our subject.